Okay. We'll do a quick revision of yesterday's class, and post that we'll look at some new topics. Alright, so we discussed about random variables. We said that we have different kinds of experiments, like tossing a coin. We could get a heads. If we flip 3 coins, the sample space is bigger. We have tuples of length 3. So if we had to write the probability of getting 3 heads, we might write it as probability of head, probability of getting 2 heads, HHT, HTH, THH. We have to write all of those events. And then we ask the following question: if we have 20 flips, we flip the coin 20 times, we want to get the probability of getting 7 heads. It's very difficult to enumerate that. Instead, we said that we will be using something known as a random variable, which is a function, not necessarily just a simple variable. It's a function which maps from the events in the sample space to numbers on the real line. We took some examples. If we have the sample space of the coin being flipped 2 times, so we have HH, HT, TH, and TT, we map each of these events, HH, HT, TH, and TT, each of these tuples, to a number. The mapping we're doing is by looking at the function which counts the number of heads. So therefore, in HH, the number of heads is 2, 1, 1, 0. And now if we have to calculate the probability, so we have to calculate what is the probability that the random variable x takes the value 1. If we have to calculate this probability, we'll have to go back in the event space. X equal to 1 lies in the translated space. We do this x inverse and look at this value 1. What events give you the value 1? So there you get the values of HT and TH. So therefore, if you have to write probability of x equal to 1, you write the probability of, you write that set as all the epsilon, where x inverse of x inverse of 1, where x of epsilon gives you 1. So therefore, that becomes probability of HT and TH, that is 2/4. So we said that to calculate the probability, we have to go back in the sample space. I said this is a bit cyclical in the proposition, and it's a little wasteful that way. But in today's class, we will be studying a topic called probability mass functions, which will make these calculations easier. We will be looking at some practical use cases of using random variables. We stopped yesterday's lecture at this point. Okay, so we've defined the probability mass function of a random variable x. So it's something which is associated with the random variable x, which is a function which will specify the probability of obtaining a number x epsilon equal to a. So therefore, if we say that px of a, this is equivalent to the probability that the random variable x takes the value a. In our previous example, we were looking at, let's say, a equal to 1, which is probability of x equal to 1. Corresponding to that, you had the events HT and TH. Corresponding to that, px of HT and TH was what number? 0.5. So therefore, we want to assign the probability of obtaining this a, of this number a, which is the state of the random variable. So therefore, if you notice carefully, we have 2 kinds of functions. The first one being the random variable, which maps from words to numbers or from the events to the real number space. And then the function px, which takes a mapping from x equal to a to a probability. So the important thing between x and a is that x is the random variable which can take multiple states, multiple values, and a is at one of those states. For example, for the coin toss, coin being flipped 2 times, what is the random variable x? X, the random variable x, is the number of heads that you obtain in 2 coin flips. Whereas, what are the possible states that you can get? A equal to 0, A equal to 1, A equal to 2. So therefore, the random variable x can take 3 states, which are denoted in using this a. So therefore, another way of interpreting random variables is that they end up giving you random values, they have multiple states. They can give you random values. They can give you different values, not exactly random per se. They follow some rules, but they have multiple states. Now, if we were to create this probability mass function of this random variable x for the coin toss experiment, for x equal to 0, we know that we have to go back to the event space and see that the events which give you x equal to 0 are the tt, which corresponds to one event out of the 4 possible events. And for x equal to 1, we can get th or ht, which will be 2. The number of elements in the set is 2. So therefore, the probability of px of 1, or the probability mass function for this random variable x. So this is how we interpret probability mass function given by p corresponding to this random variable x taking a state 0 is the probability that the random variable x takes the state 0, which you can find out by doing the inverse mapping. Similarly, the PMF corresponding to the random variable x taking the state 2 or the value 2 is the same as the probability that the random variable x takes a value 2, which is the same as going back in the event space of the probability of the event HH, which is 1 over 4. So using this, we have now fully specified the probability mass function for this random variable x, which is counting the number of heads in 2 coin flips. Now, another interpretation of random variable versus a regular variable, which we have studied in other courses, or we have studied that in elementary maths. So if you have to write 2x plus a equal to 0, if a was fixed, if a was 1, in this case a equal to 1, we'll get x equal to minus half. So in that case, there is no randomness. The number of states or the number of values which x can take is a single value, which is just 1. And a PMF is not really applicable because you're taking a single value. Whereas if a also had multiple states, if a could take the value 1, or a could take the value 0, or a could take the value minus 1. In that case, we can say that a has randomness and x is a random variable. So you can get x equal to plus half, 0 and minus half. The number of states that x can take in this case is 3. And in this case, we have assigned a particular probability mass function for this random variable x, taking the different states small x equal to plus half, 0 or minus half, all of them having equal probability. For x equal to half, 0, minus 1. So therefore, you can see the differences between a random variable and a non-variable variable. The crux being that the random variable can take multiple states, and those multiple states are also distributed as per some probability distribution, which we call as the probability mass function, PMF. Now, we have studied histograms earlier. They give you the relative frequency counts, or just the frequency counts if you don't normalize them. In this case, you're seeing the frequency of 26 English letters from the English language, maybe through some particular source. You could also give so you could do various kinds of experiments. So let's say if I tell you to count the different characters in the numbers, when you write down the numbers from 1 to 1000, how many times will you get a Z? Do we get a Z? If we write 1, O-N-E, 2, T-W-O, 3, T-H-R-E-E, do you ever get a Z? Do you ever get a Y? 30, 20. Do you ever get a L? 12. Okay, good. Do you ever get a F? 5. Do you ever get a C? Okay, so it's a good mental exercise just to wake you up. After you have figured out what histograms are, we need to understand the relationship between histograms and the probability mass functions. Can anyone guess what is the relationship between a histogram and a probability mass function? In this case, if we look at the histogram and we're looking at the relative counts, so therefore if we sum up the heights of all the bars, they will sum up to 1. You're saying that your English alphabets will take these 26 values. So this is a histogram with relative frequency counts, which will sum up to 1. what is the relationship between this and the probability mass function? So does anyone want to try that? Some students say both are same. They are going to be same under certain conditions. So to understand that, let's look at this fair dice experiment. We throw the fair dice multiple times and you note down the head. You note down the top face. If you did this experiment 100 times, you will get 1, 2, 3, 4, 5, 6. This is, you'll get, now we can actually do this experiment and show you. The probability mass function of a fair die would be 1/6 of a fair die. We said it's a fair die, so each of the outcome 1 through 6 is equally likely. Now if we were to do an experiment, and here I'm going to randomly find out an integer between 1 through 7, and I'm just doing the value counts and normalizing to make the sum up to 1, and after that I'm plotting it. So if I did, okay, so I need to run this again. Okay, so if I ran this experiment 10 times and I noted the number of times I got a 1, 2, 3, 4, 5, 6, I am showing the PMF in this yellow-orange shade, and I'm showing the histogram, which is showing the relative counts in this blue. So we can see that we are getting, out of the 10 times, 2 times we get a 1, 2 times we get a 2, 1 times we get a 3, and 1 time we get a 4, and sorry, I should be looking at the histogram, yes. So 2 times I get a 5 and 2 times I get a 6. So 2 plus 2 plus 1 plus 1 plus 2 plus 2 is 10. So therefore the counts are correct. Now can you see that there is some gap between the PMF and the histogram? Now let's repeat this experiment. Instead of 10 times, if you threw 100 times. Now can you see that this gap between the blue and the yellow-orange bars have reduced? Now if we did this experiment a lot more number of times, 50,000 times, can you now see that the gap between them is further reduced? If we did this even more number of times, 1 more, 0 added. Can you now see that the gap is almost 0 between them? Let's do it one more time. It might become a little slow, but we'll see. Okay. Can you now see the gap is almost tending towards 0? So what can you conclude from this? As n approaches infinity, the histogram, which is obtained from the empirical data, the counts obtained from the data observations, would match the probability mass function, which is the ideal distribution. So the PMF gives you the ideal distribution, which you would expect for a fair dice, and the histogram is what you get from counting the number of times these different die faces occur. And you can observe that with n tending to infinity, the histogram is approaching the PMF. So therefore, we can conclude that the PMF is the ideal version of the histogram. So now we look at why we should be studying PMF. This is a small typo from the original author. It should have been bother and not border. So why should we study the PMF? We can look at multiple reasons. The first is you want to model the ideal behavior. We have just now seen that the empirical behavior is modeled by the histogram. You do the experiment a lot of times, and then you get the different counts, and then you do the relative frequencies. But if you want the ideal behavior, then that you get through the PMF. The histogram is also known as, it's also known as non-parametric, which is to say that the number of parameters to express the histograms can change with the data. But with the PMF, it remains constant. I would not, at this point, go deeper into parametric versus non-parametric. We'll probably study them when you study machine learning. The generator view is very important. we can use the PMF. Because now we know the PMF, we know the ideal distribution, we can synthesize, generate some data from that PMF, sample the PMF, synthesize some data, and test how our algorithm will perform. So we'll do some experiments in a couple of minutes, in 5 minutes. Before that, we will just finish what a PMF is. We'll do some experiments around this. Which PMF to use for which random variable, which kind of random variable, we'll see in 5 minutes. Before that, we will look at some properties of the PMF. Now, if we look at all the possible states which the random variable x can take, and if you sum over the PMF functional values over them, you'll get a 1. Does it make sense? So you can prove this going by the actual definition of what does x equal to x means, random variable x taking a state x, where the x you're taking in is from x of rho. What does x of rho mean? What is rho? Rho is your sample space. Once you apply the function to any event in the sample space, you get a number. Let's say with a coin toss, when you did the coin toss 2 times, your sample space was HH, HT, TH, and TT. If you applied the random variable x, the mapping random of the random variable x onto that sample space, you get the output of 0, 1, 2. So small x can take the value 0, 1, 2, and that is what you're summing over. So you're trying to sum p of capital X equal to 0 plus capital X plus p of x equal to 1 plus p of capital X equal to 2. That is what this whole expression means. And we saw, at least from the previous experiment, it was 1 over 4 plus 1 over 2 plus 1 over 4. So they did indeed sum up to 1. You could actually just express it in terms of going back to what does p of x equal to x means. That means you choose an event epsilon belonging to the sample space for which the x of epsilon equal to small x. That's the definition of p of x equal to x. And you can then take the union over all the different events in the sample space, which will eventually give you the entire sample space whose probability is 1. So therefore, through this way, you can prove that the PMF satisfies this condition, that the PMF of the random variable x, which can take the different states small x, when you're summing over the different values, the different states which the PMF can take, you get the value 1. We will now take a couple of minutes and try and solve this question. You are given x, which is a random variable with a particular PMF. The PMF corresponding to the random variable capital X, taking a state k or a value k, is given as c times 1 over half raised to power k. Can you find out c? Okay, I think most of you have figured it out and have got the answer 1. So the way to solve this is, you now know, as per this property, that summation of p capital X of small x function is equal to 1. So if you just substitute these values, you will get c to be 1. I leave the formal proof, the full proof, as a homework exercise. This is fairly trivial. You just have to substitute the values and put c. Let's look at the next question. For this random variable, can you find out the value of c? How many say 1? Is this a valid PMF? No. Because for certain values of k, you're saying that the probability is negative. So therefore, don't solve this question, just stop at that point. If you ended up solving that question, you'll end up showing something like 0 equal to 0 or something, which is wasteful. But therefore, this is the reason you should first importantly know the rules of the game. Probabilities are non-negative, so therefore this is not a valid PMF. You just stop at that point. Okay, so having looked at a few examples, the need for PMF, we will actually now go and look into something more practical. how many of you have heard of the Bernoulli distribution? I've asked this earlier, but okay, so roughly 30% of you have heard, or 30% of you are raising your hands. So I also need to know the conditional probability of raise hands given that you know about it, which I would assume is a very low number. I believe if some of you know, then most of you would know Bernoulli distribution. Now to understand this, we will be defining our x as a random variable. We will be calling x as a Bernoulli random variable. You're taking, x can take one of two values, 0 or 1. So for today's class, the remainder of the things we are taking are random variables can only take discrete set of values. Can you give me some examples of applications where you get the output as a discrete value? Dice. If you roll a dice, then what can you get? You could, no, dice. Okay, you can get even or odd. If you say that x is a random variable which tells whether if you throw one dice you get an even or odd, then how many options does x have? 2 options. Okay, that's one kind of a random variable where the output is binary in nature. Can you tell me some other kinds of random variables where the output is still discrete but not necessarily binary? Sorry? Can you be louder? Head or tails is the same, like it's still binary. So I've covered one category of such outputs which is binary. Your output can be binary, either 0 or 1, even or odd, heads or tails, spam, no spam, disease, no disease. So all of these are examples where your output can take 2 values. It's known as binary random variable. Sum of the 2 dice, okay, or the number of heads you can get if you toss the coin 2 times. So in that case, if you toss the coin 2 times, then what all values can the random variable take? 0, 1, 2. Is it binary? No. It can take 3 values in this case. We call it categorical. You can have, your output is still discrete. You still cannot have 2.5 or 7.8. You still have discrete values. We call it categorical. Any other examples? Drawing a playing card from a deck. Okay. And what is the random variable x? You're telling the experiment. Okay, if you want to tell which, whether it's a club or it is a spade or it is a heart or it's a diamond. You want to tell, I don't know what that exact term is called, but you want to know that particular attribute of a card, which of these. So that's again a type of a categorical random variable which can take 4 values. Okay, any other random variable comes to your mind? Which is still discrete in nature. Okay, so let's go over them one at a time and hopefully we'll see some more examples, some real world examples also we'll say. We'll define the first kind of random variable, which is a Bernoulli random variable. X can take 2 values, either 0 or 1. We've said success or failure, heads or tails, disease, no disease. And we have to specify this. So we have to then also specify its probability mass function. We'll say that the random variable x can take 2 values. We had 2 possible values, 0 or 1. It takes the value 1 with the probability of p. Therefore, it has to take the value 0 with the probability of 1 minus p. So therefore, to define this Bernoulli random variable, you need a single variable which is p, which is the probability of getting a 1. Probability of success, probability of heads, probability of disease. So that's typically how we mention this. And we said that if we flipped a coin with the probability of p of landing heads, then x will be the random variable which is 1 if the coin lands a head and 0 if the coin lands a tail. We can also write the probability mass function of this Bernoulli random variable as this using the switch case. Probability mass function of the random variable x taking the state x where x is 0 or 1 is 1 minus p and p. So pretty straightforward. We can also conveniently write this as p, the PMF of the random variable x taking the value x is p raised to power x into 1 minus p raised to power 1 minus x. Think for 10 seconds and convince yourself that both these are the same. If x takes the value 0, what do you get? P of 0 is 1. 1 minus p raised to power 1 minus 0 is 1 minus p. So therefore at x equal to 0, you get p x of x as 1 minus p. If x is the value 1, then you get p raised to power 1 into 1 minus p raised to power 1 minus 1, which is something raised to power 0, which is 1. So therefore that becomes p. So therefore you can convince yourself that both these are the same. Importantly, we mentioned that p has to be between 0 and 1, and it can actually be not necessarily less than and less than, it has to be less than equal to also. P can take exactly 1 and p can take exactly 0 also. We then write this random variable. X is distributed. The symbol which is in math, we write this as similar. In LaTeX, we write this symbol as similar. We write x is distributed as per the Bernoulli distribution with the probability of success or probability of class 1 being p. That's how we read this statement out. Now we can plot the PMF of this. It's very straightforward. For p is equal to 0.3, you'll see that the probability of getting a 1 is 0.3, probability of getting a 0 is 0.7. So nothing sophisticated till this point. This is probability of getting a 1 is 0.8, therefore the probability of getting a 0 is 0.2. Now, how do we model them using computer code? So we'll be using torch distributions for doing this modeling. I am specifically using torch distributions. Okay, does anyone know why we're using torch distributions when NumPy and SciPy could have also sufficed here? Yes, any thoughts as to why we're using torch distributions when I could have used numpy.random.random or numpy.random.binomial or .Bernoulli? Yes.
You mentioned something about them using a seed and not being trivial. Is that the reason?
No, so all of them are indeed randomized, full randomized algorithms. I mean, they'll give you the proper PDFs, probability distribution and probability mass functions. My reason for using torch is just that the uniformity in the interface, which is provided across the different distributions, and the kind of attributes we'll see. So we'll just see in a couple of minutes what torch does. I want to define this distribution, Bernoulli distribution. So I call dist distribution object equal to torch or distributions.Bernoulli, and I put a question mark, which is my way of checking the syntax. You can see that I get the doc string. It tells me that I can create a Bernoulli distribution object where I can either pass something known as the props or I can pass something known as the logits. Does anyone here know what a logit is? Okay, hopefully by the end of this lecture you should know something about logits. So it creates a Bernoulli distribution parameterized by either props or logits, but not by both, either of them. For now, we will just be using the probabilities. So I create a Bernoulli distribution object with probability p equal to 0.9, which means the probability of success, probability of heads, probability of class 1, probability of everything you called 1 is 0.9. So therefore the probability of 0 is 0.1. I say dist equal to torch distribution.Bernoulli props. I can just print out this variable and see what I get. So it prints out the probability, which is 0.8999, which is just floating point imprecision. This is just 0.9. I am also I just call this dir function. I don't know if you've seen this function earlier or not. Dir function will give you all the different attributes which are associated with this object, dist object. And I'm removing the one which start with underscore. So if I had instead not done this and I just called dir of dist, I get all of these: class, del attribute, dict, less than equal to, etc., etc. I don't want all of them. I just want to look at a few attributes. This is just to show that what all attributes does a PyTorch distribution object have. Not all PyTorch distributions will have all of these, but you'll have many of them across different distributions. You can see things like CDF, which we'll study, which is known as a cumulative distribution function. Entropy, which is an information theoretical concept defining how much variance is in the data, how much information is there in the distribution. You can look at something known as Logit's mean mode perplexity. This is not the company perplexity. This is some other information measure similar to entropy. You can call the function sample to draw some samples from this distribution. You can look at the support. Okay. So my distribution had a mean of, not a mean, sorry, the probability of heads was 0.9. If I call dis.mean, the mean of my random variable is 0.9. Now, this is to show you what all attributes we can study. In a future class, probably the next class, we will study what is an expectation. And if you calculate the expected value of the random variable, you'll get the same value as dis.mean. I want to show the code first, and then we'll go on and derive these things in maths. So you can see that dis.mean, or the expected value of this random variable, is the same as p. This dis.probs is also p. Okay, does anyone here know what a support of a random variable means? Anyone? What do you think the support of a random variable means? Okay, so let me define it and then you tell me the answer for this particular distribution. The support means the different values which a random variable can take. So if I call dis.support, what do you expect to get as an output? 0 or 1. PyTorch distributions nicely has encoded this and says it's a Boolean. So it's a 0 or a 1. So therefore it's a very nice, convenient kind of functions that they have provided, attributes they have provided. I am now calling this function dis.logprop of 1 and I'm exponentiating that. What do you expect to get as an output? 1, 0, 0.9, 0.1. 4 options. How many say it's a 1? Can you raise hands? How many say it's a 0? How many say it's 0.9? So it's only 4 options. You don't lose anything apart from just moving your blood slightly above your head. So let's do this exercise again. How many say it's a 1? How many say it's a 0? How many say 0.9? How many say 0.1? Okay, the others still don't want to exercise. We get a 0.9. So what this is telling me is, this is equivalent of what is the probability mass function evaluated at the value 1. Or we go back to the definition. This is equivalent of saying what is px when x equal to 1. That value is p, which is 0.9. Now, they don't directly give you this PMX, this PMF. They give you the logarithmic of it, and then you can take the exponentiation of that. We'll again study why this is the case, why they don't directly give the PMF, but rather give the logarithmic of that, which we then have to exponentiate. But importantly, you can see that we can now see that what is the probability of getting a 1 given this random variable specified by this Bernoulli random variable. So it's 0.9. Similarly, if I give distribution.logprob of torch to 10 to the 0 point exponentiation, what do you expect to get? 0.1. Okay, what do you expect to get with the value 1.5? How many say it's a 0? How many say it's a 1? How many say it's undefined? Why do you say it is undefined? No, not because of log of 0. I mean, we don't even get to that stage. You're correct that way. What was the support of the function? What was the support of the random variable? 0 or 1. It cannot take anything other than 0 or 1. It's as simple as that. So therefore, it's important to understand what is the support of your random variable. If I tried giving 0.5, I just passed this in a try-catch block. So I get expected value to be within the support of the distribution Bernoulli. And we found out invalid values. So therefore, you cannot evaluate the probability at places which are not within the support. Now we come on to the more fun parts. We can call this dot sample method. If I call it once, I get a 1. Let me call it again, I get a 1. 1. Okay, how many tries do you think it will take me to get a 0? How many think it will take me 0? 1 try, 2 try, 3 try, 4 tries. So some say 10 tries. Let's do that. Okay, not this. 2, 3, 4, 5, 6, 7, 8, 9, 9. Sorry?
You got it in the second one.
Second one? No, I tried it 9 times. I was running.
You got it.
Oh, I got earlier also? Okay. So this will also be a question that how many tries do I need to succeed or fail? We'll see that. We'll also model that as a distribution. But for now, we were seeing that the samples you're getting is either a 0 or a 1. Why is that? Because the support of this Bernoulli random variable is Boolean, which is 0 or 1. If I generated 1,000 samples from it, this is equivalent to tossing the coin 1,000 times. So I'll get 0, 1, 0, 1, head, tail, 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 head, 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 something like that. So you can look at the first 10 samples. They're all 1, 1, 1, 1, 1, 1, 1, 1. Okay, if I did samples.mean, what do I expect to get? 0, 1, 0.1, 0.9. 0.9. We'll get around 0.9 good. We will not get exactly 0.9 because this is generated from the data, which is equivalent to the fact that this histogram is not the exact same as your PMF. That's another interpretation you can see through this also. Okay, I think this one we have already tried. Let me get rid of this. Okay, so now we'll go on to the next question. How many of you know the difference between lime and lemon? Can someone tell me? Someone who's not answered earlier. Okay, so which one is the lime here? The green one is the lime and the yellow one is the lemon. So what can you see apart from the color? So let's assume all of them have seeds and we don't have the seedless variety. Which of them is smaller? The green one or the limes are generally smaller, the lemons are generally bigger. And we can also look at the shapes. The limes are generally small, green, and they're more tart than lemons. So you're talking about the taste also. The lemons are generally larger, oval-shaped, and yellow. Nutritionally, they are identical. We look at the colors, etc. Importantly for today's class, we will say that lemons are generally 2 to 4 inches in diameter and have a more oval or oblong shape, whereas limes are generally 1 to 2 inches in diameter. Now we want to be looking at this problem of given a particular fruit of a particular radius when we're given a particular fruit of any specific radius. So we're given a fruit, it's either lime or a lemon, and we're given its radius. We're not given the color, we're just given one attribute of it. We have to predict whether it's a lime or a lemon. We will say that the radius of the fruit is small r, and the type of the fruit, y equal to 0 is lime, y equal to 1 means a lemon. So then what is the support of this particular random variable that we'll be using? Boolean, 0 or 1. So therefore, would something like Bernoulli random variable make sense? You can take 2 values. We want to model the specific probability, which is the probability of a fruit being a lemon given the radius, which means we want to model this probability of y equal to 1 given that you have a particular radius. And so we are looking at this specific conditional probability. Folks, can we please remain silent? We'll be looking at this particular probability. Now in the slides we discussed that it is it's important to consider the generative process. So therefore we look at the generative process today. Now, if you were sleeping till now, I would encourage you to wake up, or if you are genuinely friends with your friends, to wake them up now because this is slightly harder. I teach some of these things in machine learning, but I just wanted to give you a preview at this stage so that you get a more practical sense of why we use random variables rather than just the coin toss experiment, which does not really add a lot of value beyond just the educational perspective. So if you want to do something in more advanced subjects and want to understand how they're related to probability distributions, now is the time to wake up. We will be using some manual seed to specify the seed so that the experiments I do are reproducible. I will generate some radius. I will generate the radii of these fruits from something known as a uniform distribution, which means that I will be generating 1,000 values whose radii are between 0 and 3. So I can draw any value in between 0.1, 0.3, 0.7, 0.8, 2.9, 3.0. What is the support of this distribution? 0. No, the support is not infinite. Can you draw value infinity from this distribution? No. So the support means what all are the plausible values you can draw from a distribution? What all can you draw? Real numbers between 0 and 3. That's the support of this random variable, this probability distribution. So if I look at the radius of my different fruits, I get something like 2.6, 2.7, etc. till 0.399. The reason I'm modeling it in this specific way is because I knew this, that the limes are generally 1 to 2 inches in diameter, so 0.5 to 1 inches in radius, and the lemons are generally 1 to 2 inches in diameter. If you get a fruit of 1 inches, are you sure, of 1.5 inches, are you sure it's a lemon? If you get a fruit of 1.5 inches, are you sure it's a lemon? No, you can have, it's very likely that it's a lemon, but it's not guaranteed it's a lemon. So that is the reason why we are using these probability distributions. I am also looking at the radius, histogram of the radius array. So it's uniform. I have a lot of fruits ranging from the radii being 0 inches to 3 inches. Now we'll be using the generative process for modeling this data. You don't need to follow the entire process. Just assume whatever I'm saying is correct. We'll say that if some w into r plus b is greater than 0, where w and b I am defining, I know the radius. If I know w and b and it's greater than 0, then I will tell it's a lemon. Otherwise, I'll tell it's a lime. So does this look more or less correct? So if w is positive, if b is negative, and wr plus b greater than 0, I say that it's a lemon. So if I increase r, it's a linear function. You can see wr plus b is a linear function. If I increase r, then my value wr plus b will increase, and that becomes more chances of becoming greater than 0, which means that more chances of being a lemon. Right? So I'm just saying that wr plus b greater than 0, it's a lemon, otherwise it's a lime. I will assume some values, w true equal to 1.2 and b true equal to minus 2.0. And I'll define this linear transformation, which is just wr plus b. Now I mentioned something at the starting about logits. I'm using another variable here called logits. Without going into details, logits is some number that I get. Can you tell me the range of logits? Generally the range of logits. What space does it belong to? Is it constrained between 0 to plus infinity? Is it a real number? Is it a natural number? Is it a Boolean variable? It's a categorical variable. What kind of value can logits take? Any real number? Right, so you're not putting any constraint, so you can get any real number. For our data set, we get 1,000 values which are varying from minus 2 to plus 1.5. But you could have given any value. If you vary r, you'll get different kind of values. Now we cannot directly use logits because logits is varying from minus 2 to 1.6. You cannot directly be using logits to tell something about the probability of it being a lime or a lemon. We know that fruits which have a bigger radius, they are more likely to be lemons, but that is all I know. So I will be using something known as a sigmoid function, which maps the logits to probabilities. So I want some values between 0 and 1, which is my probabilities. So I pass my logits to this function sigmoid, and I get something known as my probabilities. And then I create this data frame where I had my radius of the different fruits, the logits which I am obtaining by w into r plus b, and probabilities which I am obtaining by running over this function 1 over 1 plus e to the power minus x. I'm not going into the details of why this function, why this is giving us the probabilities. That is to be studied in some future course. But let's assume this to be giving us probabilities. If I look at this data frame, now let's try and understand what this data frame is telling us. For radius 2.64, I get the logits to be fairly positive, 1.17. The probability of it being a lemon is 0.77. So this is the generative process. I am telling that these are the probabilities. Let's say I am nature. I am the force of nature, and I am deciding that these are the probabilities of this fruit being a lemon or a lime. Of course, I'm missing out a lot of important variables, including which tree the fruit is grown on, etc. But discounting all of those, let's just look at the relationship between radius and the probability it is a lemon. 1.14, the probability of it being a lemon is 0.35, which again sounds reasonable because it's a smaller fruit. So therefore, it's possible that it can be, the probability of it being a lemon is smaller, probability of being lime is greater. Similarly, with the other examples you can see. We can also look at the fruits whose radius is less than 0.2. You can look at these. These are very small fruits, radius being 0.01, 0.01, 0.01. And the probability of them being lemon is almost close to 0.1. So it's very unlikely that these fruits are lemon, but it's not completely unlikely. It's highly improbable, but not impossible, that these fruits will be lemons. So now I will be generating my data set. This is where I will be using the Bernoulli distribution. So I have my probabilities. This is the probability, this is my data frame. Probability of this being a lemon is 0.76. I'm defining lemon to be 1 and lime to be 0. So if this is 0.76, and if I sampled from this particular distribution, am I always going to get a lemon? Can I get a lime? With what probability? 0.24? Yes. So that is what is happening. I will have this y true, which is my torch distributions or Bernoulli object on the probabilities vector, sample from it, get my y true. This is how my data frame would look for the values where y true comes to be 1. It could be either 1 or 0. So you can see that for this example, the radius is 2.64, probability of it being class 1 was 0.76, and it turns out to be class 1. For this example, the probability of it being, so the radius was 1.17, rather low. Probability of it being a lemon was also low, but it still turned out to be a lemon. This is the generative process which I'm telling. You can generate lemons even though the probability of it being a lemon is low. Similarly, you can see for the other cases also, that we could have seen for y true equal to 0, you can see that, like this example, where the probability of it being a lemon or class 1 is high, but it's still, when you sampled, you still got a 0. Who had this example? Now I plot my data set. This is showing the limes versus lemons and the radius. Each of the line that you're seeing is corresponding to one instance. So can you see that here we have a darker region here? A darker region here means that we have a lot of limes with low radius. And for lemons, we see a darker region towards the right hand side, which is higher radius. So therefore, it means that it is much more likely to have limes with low radius and lemons with larger radius. But you can still have lemons with a lower probability when they have a small radius. You can still have limes when the radius is larger. And now I'm using something known as logistic regression, which again you don't need to understand at this point. I am trying to learn the W and the B from the data. I have this, all of this that I'm showing is the data generation process. Once I've generated the data, I can fit some model and learn the parameters. I end up learning, my true weight was 1.2, I ended up learning 1.25. My true bias was -2, I ended up learning -2.01, which is almost similar. I can also now predict whether a fruit is a lime or a lemon. So if I give the radius to be 0.5 and my model, I get that the output is a lime with the probability of it being a lemon being 0.2. And similarly, I can look at 1.5. It is also lime. With 2, it should be a lemon. So this was a whirlwind tour of how we can use random variables for practical problems in machine learning. This was one such example where the variable or the outputs are discrete. In this case, they can only take 2 values, Boolean. So therefore, we can model them using Bernoulli random variables, which gives us the probability of class 1 or heads via P, and of the other class or tails being being 0 or tails or no success being 1 minus P. So that's how you define the Bernoulli random variable, and you can use it for practical machine learning problems, data simulation, etc. Having looked at this problem, we will now be looking at the next distribution, which is known as the categorical distribution. So you can think of the categorical distribution as the generalization of the Bernoulli distribution. Bernoulli, you could take only 2 values, binary. In categoricals, you can take 1 out of the k values. We discuss the possible examples, which is it a spade, is it a club, is it so different faces of a die also we can look. We can also see what grade you'll get. Right? Again, depending on how you perform, you'll get certain grade. What are the possible values of the grade you can get? A, B, C, D, E, F. Hopefully none of you go beyond D, E, and F. But so that's again one of the few categories of grades you can get. So those are known as categorical distributions. So we say that we have a random variable x which can take one of the k possible values, 1 through k. The probability mass function is given by this probability mass function of this random variable x, taking these different states or values x equal to 1 through k, defined by these theta i's, theta 1, theta 2 till theta k. Now each of these theta i's have to sum up to 1. So if I took this whole class, and if I look at all the grades, probability of A plus P of getting B plus P of C plus P of D plus E plus F, should it be 1? Assuming everyone gets a grade. So this random variable, we write x random variable is distributed as per the categorical distribution, given this theta vector, which is the probability of it taking state 1, state 2 till state k. Like if we had a fair 6-sided die, which is fair, then what would the PMF look like? 1 by 6 for each of the 6 values that you can take. So you can take one of the 6 values and it would be the same for each of them. Now, some practical use cases for this. So previous case we looked at whether something which is known as binary classification, whether it's a lime or a lemon, whether it's a cat or a dog, those kinds of questions, whether it's a head or a tail, whether it's you will get a loan or you will not get a loan, whether someone has a disease or doesn't have a disease. Whereas for categorical, now you're looking at multiple possible outputs, but it's still discrete. So one such example of that could be image classification. If I took random photos in this classroom, then you have to tell me which of the 1,000 objects this is. What is this? Bottle. What is this? A table. So you can have, let's say, 1,000, 2,000 such possible outputs, which you can then say, I want to predict that my output is one of these classes. And for modeling this, we can use the categorical distribution. The ImageNet is a very popular data set which is used for image classification. Where given an image, You want to tell whether it's a particular type of a dog or it's a sailing vessel or a watercraft, etc. You have to give the output in one of those k discrete categories. So to understand this, we will now be creating a theta vector which is 0.1, 0.2, 0.3, 0.4. How many states will this random variable take? 4 states. It can be either 0, 1, 2, 3, 4. It's a 4, let's say it's the head of a 4-sided die. I'm giving the probabilities of it taking 0th state is 0.1, taking 1th state is 0.2, taking 2nd state is 0.3, and taking the 3rd state is 0.4. I can now define my torch distributions categorical, specifying that the probabilities is as per the theta vector. And I can print out this distribution. What is the support of this? What is the support of this random variable? 0 and 1? In this case, the nice way in which PyTorch has represented this, they have these constraint classes. So they have represented this as an integer interval between 0 and 3. You are trying to represent 0, 1, 2, 3. That's how they've represented. Okay. What do you think is the output? Dis.log prob of torch tends to 0.0 exponentiation. Let's look at this PMF. 0.1. That is the probability that the outcome 1 is chosen as per the PMF. So it's 0.1. Similarly, if you tried out 4.0, which is not within the support, you will get the output. It's not within the support. If I drew 1,000 samples, as I'd done previously for Bernoulli, and if I look at the first 10 samples, I'll get 3, 3, 2, 3, 1, 3, 1, 2, 2, 0. You see a lot more 3s and 2s because those states had higher probability as per the PMF. If I ran this one-liner, what do you expect as the output? There are 1,000 samples. We do a value count on them. So therefore, you'll get the number of zeros, number of ones, number of twos, numbers of threes. And then you're normalizing them, which means that you're looking at the fractions of them over the 1,000 examples. And then you're sorting them by the index. So therefore, you'll get 0 occurs with a fraction 0.085, 1 occurs with fraction 0.2, 2 occurs with fraction 0.3, and 3 occurs with fraction 0.4. Again, is this exactly matching the PMF? No. Is it very close to the PMF? Yes. If instead of 1,000 examples, I had 10,000 examples. Can you now see that these numbers are much closer? If instead of 10,000, I had 1,00,000, can you see that they're even closer? So that is, again, you are seeing that the histogram, this is basically the histogram because it's discrete. So I can directly do the value counts and plot the histograms. The histogram starts matching the PMF when the number of samples drawn is a very large number. So this was to show the categorical distribution, which you use in the cases when you want to do some multi-class prediction, but it's one of the k classes only. Okay, we now look at the next distribution, which is we want to do some quality control in factories. Why don't you look at this question, think for 30 seconds and tell me how would you model this? Okay, answers. How would you model this? Binomial. How many say binomial? How many say Bernoulli? How many say categorical? Can you have categorical? Because you are getting 1 through 10? No. So we want to model the number of defective chips. We'll model this using a binomial distribution. We'll say that let x be the random variable which tells the number of defective chips in the sample, where the sample is of size 10. So therefore, you can notice that X can only take values from 0 through 10. Right? So it's in some sense you can also think of it as a categorical, but it's here it will be binomial because each of the particular chip has a particular probability of failing or succeeding. So therefore, the probability mass function of this binomial distribution is given as n choose x p raised to power x into 1 minus p raised to power n minus x, where we can, p is between 0 and 1. It should be again less than equal to 0 and less than equal to 1. Greater than equal to 0 and less than equal to 1. N choose x is a binomial coefficient, which is the number of ways to choose x defective chips from the n chips. If we had a probability of failure was 0.1, which means each chip has a failure rate of 0.1. We had 10 chips. We would model this as torch distribution binomial with the number of chips and the probability of failure. And if we look at the distribution, because the total count is 10, the probability of individual failure or success is 0.1. What does this dot support? 0 through 10? It's an integer interval going from 0 through 10 because that are the possible set of values which you can draw from this binomial distribution. I am also showing okay, let me run this again. Okay, I think I need to just okay. So one failure probability is 0.3. Let's see the number of defective chips. 0 defective chips, the probability is 0.34. 1 defective chip, the probability is 0.38. 2 defective chips, the probability is 0.19. 6 defective chips, the probability is 0.00014, so on and so forth. So if I increase the precision, you will see that I get some numbers. Even there is some almost close to 0 probability of getting 10 failures, even though the probability of a single failure is only 0.1. Right? So this is similar to saying that what is the probability of getting 8 heads when the probability of head in a single coin toss is 0.1. I'm sure you have done this earlier in your earlier studies. This is a more formal way of understanding that. We define such problems using a binomial distribution. I am also now plotting the true PMF. So this is how the true PMF would look like. It is peaking at 1. Why is that the case? It's peaking at 1 because just look at what we'd given. The probability of failure is 0.1. Now, if we were to draw some samples from this, as we've been doing earlier, we look at a few samples. This shows that out of 10 times when out of a sample of 10 size, 2 failed, out of a sample of 10, 0 failed, out of a sample of 10, 1 failed, out of a sample of 10, 3 failed, and so on. So if we were to again look at these counts, they would again be fairly close to the true PMF, but not exactly the same. Similarly, we now look at a different kind of a problem. So we've looked at 3 different distributions till now. Bernoulli, where we're trying to model some binary variables, success or failure, true or false, where you get a loan or not get a loan. The second was the categorical, where you have multiple output categories. Is it a cat or a dog or a sheep or a wolf? Will I get an A or a B or a C or a D grade? The third we have looked at is binomial. What is the number of times number of heads we will get when the probability of getting an individual head is 0.1? What is the number of defective pieces we'll get in a batch of 10 when the probability of a single piece being defective is 0.1? Now we go on to the next kind of distribution, where we're trying to model something like the number of SMS received per day. Let's now change this to number of WhatsApp messages received per day. Let's say if this is your data on different days, you've been getting different number of messages. How would you model this kind of a data? Can you use binary? Is the output binary? No. Can you model it via the categorical distribution? You can, but it would be an overkill. It would be not be very well specified problem. Can you model it via the binomial? No, it's not an apt fit. We end up, so this is the actual data, the number of WhatsApp messages that one can receive. This is as per some public database. So we want to model the number of SMS messages you receive per day. We will be using something known as the Poisson distribution, where let X be the number of SMS messages you receive per day, and X will only take values from 0, 1 to some positive values only. And the probability mass function of this Poisson distribution is given as probability mass function of the random variable X, where we're looking at the probability of it taking the state X is equal to lambda to the power X into e to the power minus lambda divided by X factorial. It's a one specific kind of a distribution. We'll see more as to why this particular form comes. I'll probably also link some videos like 3 blue 1 round videos which help you derive such kind of expressions. So X can be from 0, 1 to 3. So X is the number of messages that you'll get has to be a positive integer, has to be an integer. You cannot get -1 or you cannot get 1.2 messages, where lambda greater than 0 is the average number of SMS you receive per day. That's the model parameter. So if I define this rate parameter to be 6, I create this distribution. Okay, what do you think distribution dot support will give me? What are the possible values you can get from this? What is the number of SMS you can get on a given day? Can you get 0 messages? Can you get 1, 2, 3, 4, 5, 6, 7, 384, 50,000, 895,000? Can you get all of those values? The latter values are very unlikely, but you can still get them. So therefore, what is the support of this distribution? It's not infinite. Non-negative integers. So that's how we define the support of this. We can then also plot the PMF. We said that the rate parameter is 6. So on average, we'd expect to get 6 SMS or WhatsApp in a day. And now we're looking at the probability distribution. What is the distribution of getting 0 messages? It's a low number of getting 6 messages, of getting 5 messages, of getting 16, 17, 18, 19. I've just clamped it to 19, but I can technically go till infinity, but all of them have to be integers. You can see that my expected rate of getting SMS is 6. That's where I have a peak. It will be an interesting exercise for you to work out why these two look so similar. Is it a bug in the code, or do you actually get this behavior? This was when you are trying to count different kinds of events. That's where you use the Poisson distribution. Let's say if you are in a mall, you want to count the number of people who are entering into the mall at that any particular hour. The number of students who leave the classroom in between the lecture at every 5 minutes. So I can model that as a Poisson distribution. It will be a non-negative integer. Hopefully it will be, it will be a non-negative integer that's not likely to be 0. So once I have that specific rate, I can model that. Now for the final distribution which I want to teach, it's the number of sales calls you have to make before you do a successful sale. But let's say you're a sales representative, you're making a cold call. Does everyone here know what a cold call means? Anyone who doesn't know? Anywhere, so has everyone here, anyone who's not seen The Pursuit of Happiness? Okay, how many have seen The Pursuit of Happiness? What does that person do in that movie? Makes cold calls for trying to sell that huge computer-like device. It's actually a medical-grade device. So let's say that you are Will Smith, like whatever he's playing in that movie. You're you want to model this probability of the number of calls you need to make before you get a successful sale. So each call has a probability of P being resulting in a successful sale. So therefore, for each of the individual calls, you can still use the Bernoulli distribution, which is what is being used even in binomial when we make that assumption. We want to model the number of calls needed before achieving successful sale. And this is done using a geometric distribution, where X is the number of calls needed before achieving a successful sale. And then X can again take values from 1, 2, 3, 4, and so on. The PMF is given by this 1 minus P to the raised to power X minus 1 times P. So if we took P equal to 0.3, the probability of each call resulting in a sale is 0.3. Then how many calls do you need to make before you get a successful sale? Distribution is this Torch distribution is a geometric of P. I can look at the distributions. The support, like Poisson, is non-negative integers. If I were to do a sample of 10, so what this means is that I need to make 5 calls before I get a successful sale. I need to make 7. I need to make 1. So therefore, you can again just mark or plot the PMF of this. You can also draw some samples and then try and get some data and then try and understand how the histogram is comparing to the PMF. So therefore, in today's class, we have looked at this important subject matter where we are trying to understand, given a real world scenario or given a machine learning or data visualization or a data science problem, what important is the support that you have. That's the first thing you want to see. Once you know the support, then you want to see that what is an ideal distribution you want to take. Correspondingly, you decide and design the random variable. And from that, you assign that respective probability distribution. So therefore, if you now go back to the question which I asked in the previous lecture, right? So here we said that we need to go back to the event space to then figure out what is the probability of 2 heads, 3 heads, 4 heads, 5 heads, etc. Now, what is your response if I ask you this question? Do you need to go back to the event space, or do you know that certain kinds of experiments are distributed or can be characterized or modeled as per some probability distribution? In this case, you could either use binomial for certain kinds of experiments, or geometric, or Bernoulli if you have single coin tosses or single coin tosses. So that to me is the more important aspect. In the next few lectures, we'll study some statistical properties like what is the support, what is the expectation, what is the variance. But from today's lecture, I would say you should go from today's lecture to the future lectures, not go from theory to practical. This should hopefully help you understand and appreciate why we need random variables. Thank you. Any questions?